an integral is a sum, it's indicating accumulation. And that's why the way to calculate that, right? We strictly gotta learn how to use, we're gonna have to learn how to use the summation. So let me just introduce for you guys. So after we learn about what an integral is, right? Let's look at the summation notation. Let's look at what a summation notation. The simplest way of putting it is, well, a lot of times you have a lengthy sum, right? Like a very lengthy sum with 3 terms is just not too short, right? You're talking about a sum with 100 terms and all, and then even more. So in summation notation, you got the idea is term number 1 plus some term number 2 plus some term number 3, right? And keep adding it until you get some last term. So you got some n term right here. So repetitively enough, we keep repeating the adding, right? We keep repeating the adding. That's why for convenience, we're going to write it as a summation. Because all of these, adding up all of these terms from some beginning to some ending like that, we use a summation notation. Each of these terms stays at some index. That's why it's now generally in a summation formula, right? It stays I. Okay? And then the I runs from 1 to n. So this is the ending, and this is the beginning of your summation. Okay? And so, quick example, just to get comfortable over here. Then, let's just learn to write out the terms, right? The summation. Okay, so when you're looking at something like this, you got a sum being I, right? 1 to 10, for example. Okay? Here's how I'm writing it down. I'm talking. So this is right now, it's an entire sum, but then it's written as start in the summation notation. So the question, the example wants you to write down the terms, right? All the terms. So that means what? First term of this sum. So the way how you're reading, right? I runs from 1 to 10. That means the entire sum here got 10 terms altogether. See what I'm saying? Now 10 terms, right? Because if you're counting 1, 2, 3, 4, 5, right? Up to 10, there are 10 terms together. So first term, when you're writing it down, the first term is when I equals 1. So when I equals 1, it's going to be 1. So 1 is your first term. Term 2 is going to have to be 2 because that's when I equals 2. Okay? Term 3 is going to be 3. And so each term here has value determined by I. The value of the term determined by I. So we keep writing down the terms until you reach 10. So keep adding like that until the last term of yours is 10. Okay? That's how we're writing it. So the I here, so the way how the summation notation works is that in your general expression right here, it gives you a way to express the term at each index position, at each of the indexes. So I'm talking about if we're at the 5th term, right? And that means the 5th term is 5. Okay? So another one to try here. Think about a 3n minus 3i minus 1. Right? I 1 to 5 here. Okay? We call it part B of the example. So, again, this summation here is indicating we're going to have 5 terms, right? First term got value 3 times 1. See, first term, the I index equals 1. I index equals 1. So first term is 3 times 1 minus 1, according to that general setup like that. The second term is 3 times 2 minus 1, because here is the second term, I equals 2. That's the idea of that. Okay? And then we're adding those terms again. And then the next one here, 3 times 3 minus 1, right? That's 3 times 4 minus 1. And the last one here is 3 times 5 minus 1. So now really the real sum, the first term right here is going to be a 2. You guys repeat that? Right? The next one here is going to be, that's making it 5, right? That's region 2, 6 minus 1 is 5. The third one here is going to be 8, right? The next one here is going to be 11. And the next one here is going to be 14. Well, so, you know, so that's how we write down the terms. These are the terms here. These numbers are here for the terms, right? These are the terms. But then being 2 on the first term, being 5 on the second term, those are the values of each term, right? The 2, the 5, the 8, those are the values at the term, right? And then the final answer. So in the end, it's a summation. That means you can, once you write down all the terms, you have your right to add it all up, right? You add it all up right here. So the real final sum for this, right? The real final total is going to be, you go ahead and add it up for me. It's probably 40. Just add it up. Just add it up. Don't say probably.
Mental math, it's degenerated.
Okay, it's 40. Okay. So this is the real final total sum, right? This is just writing down the sum written down with the term here, but this is the real final sum here. You guys follow with me on that? Okay? So what about this sum? It's easier. These are the terms written down, but what's the final total sum?
55.
What's that?
55.
55? Yes, should be 55. Right? So now that's just 10 terms, right? It takes some time adding up. 5 terms, you can see it also takes some time adding up, and it's starting to get way beyond our mental math capability, right? Right? But that's something that we are heading in right now. So let's look at example 2. Another example where you guys try to get comfortable with writing down the summation formula. Now, I want you to write the following sum, right? Right? Following sum in summation notation. Okay. Meaning the first sum I have here, you guys, how about 1 plus 4 plus 9 plus 16 plus, okay, 25 plus 36. Sound good? How many terms are there? 6 terms, right? Okay. And so, see, you got the whole sum written down in terms again, right? All the terms, we want to rewrite all of this here as one summation notation. So here's how we get it work in your formula. You just first of all count how many terms there are. See what I'm saying, no? So that means once you already recognize the 6 terms, right? That means as far as adding up the terms, see, we keep repeating the adding, right? So the I, the terms added, being summed up from its first term to the 6th term. See what I'm saying now? So this summation here includes adding up all the terms from the first to the 6th, right, being the last one. But then, what about the value? Is there a general rule you use that you can see in each of these terms here? At index, at each of the index, this is index 1, this is index 2, right? This is index 3, for example. What do you recognize about the value in the index position of the term? Yeah, it's a square, right? It's easy enough to see. So this is that summation of I squared. You guys follow it? Right? I squared where you're summing up from the first term to the 6th term. That's how you're dealing with that. Makes sense? Right? So, need another one right here. Go ahead and write that in summation notation together. 2, 4, and 6, right? 1, 2, 6. See what I'm saying now? And then these go to 3 and 5, and so this is index 1, right? This is index 2, index 3. Do you see a relationship between these values and the index itself again? And of course, I mean, it takes some creativity and practice to see through these the challenges. When you work it down to the I formula, it takes your time practicing it, right? The more you work on that, the better it's going to get. Okay? Sounds good? So now in the end, a sum itself, I mean, no matter summation, notation, or whatever, it's just a sum, right? It's just a way to write a sum. In the end, anytime we have a sum, the whole final purpose is to add it all up, right? And so, let's say we learn to evaluate, right? call it example 3 right here. Okay. Let's just find the value of the sum following sum, right? But really without adding the terms. So something like this is what I mean right here. When you have like the I from the example we had yesterday, and when I went from 1 to 10, yeah, okay, we can technically we can still go 1 plus 2, right? Plus 3, plus 4. This is how we write it down. Plus 5, plus 6, and so on, up to plus 10, right? And then we sit in there and start adding up the terms, right? And we go all the way to the end for adding from 1 plus 2 plus 3, and so on. But now, see, with things like that, if I could just bring it back in here, but now I'm going to go, hey, go from 1 to 100 right here. Good luck with adding the terms. See what I mean right there? Okay. It's the same exact sum. It's just a lot longer. Right? It goes all the way up to 100. So yes, adding the terms can be okay, but see, I'm not forcing you to go without adding the terms. But if we really want to spend time adding the terms, then good luck with that. Because it's going to be taking a lot of time and effort. Okay? And so in this case here, now we're going to have to start utilizing a couple of the things from our past understanding. And actually, I'm not even sure if they taught you guys this formally or they were letting you guys, I mean, your prerequisite courses like that. Because it's a very new material. So the idea now that when you have this specific sum, summing up all the terms I, where each term here, the value equals the I position, like the one we have right now. But then we're adding at some n index there, right? But instead of adding up like 1 plus 2 plus 3 up to plus n, right? Instead of doing that, you can do the following. N times n plus 1, right? Over 2. That gets you a total sum without adding up the terms again. Okay? And so like I said here, we don't want to do that. 1 plus 2 plus 3, right? Plus all the way, etc. up to 100. Even writing it down, it takes a lot of time, right? And then so good luck with adding like that, but really all of these, after adding up, will come out into 100 times 101, right? And divided by 2. See what I mean? Because 100 is the ending of our sum, because the last term, I mean the number of terms again, right? And then we multiply with one consecutive number over, and then divide that product by 2. Okay. And so go ahead and this time here you can use a calculator and do a quick calculation of that. Okay. When I get to that, I'm not better than anyone. Alright. But see, at least it's better than sitting down and adding up the terms, right? And typing it into a calculator. It's still going to get a lot of time. So now we've got a quick answer. So you guys see the purpose of introducing this formula right there? Alright. And so, just like that, we got another one. So in the same kind of problem right here. And now you definitely need to Google search a little bit sometimes. Your textbook also has this one right here. But when you, so think about I squared right here, right? And I is going from 1 to 10. It means you go, if you're adding up the terms, you go 1 plus, 4 plus, 9 plus, 16 plus, 25, and so on, up to 100. You guys all know that. There are 10 terms. 10 terms, right? But these are the values at each term of that. But you definitely don't want to sit there and keep adding up. Right? 10 terms is still a lot with those numbers. It's hard to keep track of. You want to say that? Okay? And so with this special one right here, your textbooks, any textbooks actually, and even Google website has a formula for this. So instead of adding up the terms, but remember, each term in your sum right here is in the square form, right? The square of the index position. And so here we go, n plus 1 times 2n plus 1, right? And over 6, actually. that way, I'm looking now at for this summary in particular, we got 10 terms equivalent to the n like that. And so, without adding, right? Adding up all of that, it will give me 10 times 11, right? That's 10 plus 1. Yeah, and then 21, that's 2n plus 1, 2 times 10 plus 1, right? And we divide that by 6 again. See what I mean? 385? So we're adding it up without adding the terms, right? We really didn't add the terms, but that answer comes up equals the sum. You got the idea of that so far? So how about if you have a summation that goes like this? So I goes 1, 2, pick a number for me, pick a number for me. 9?
5,296.
296?
5,296.
5,296?
Yes.
Okay.
I don't know why this.
Okay, there you go. Your term sum, I mean your sum terms are all just constant term 2. Okay? You make for yourself a huge challenge. It's okay, we can handle it. It means 2 plus 2 plus 2 plus 2. How many times will we add per year? Yeah. We got 5,296 terms that you add. But the good news is they're all constants, right? So in that case right here, your final answer is just simply what? It's common factor of 2, so 2 times, right? And then just 1, 1, 1, 1, 1, right? 1 plus 1 plus 1, so really it's 2 times 5,296. You guys all agree on that, okay? Okay, so with this one here, technically we were adding the term, go ahead and multiply that for you. 2 times 5,296.
10, 5, 10, 6, no, 10, yeah. 10,
10.
5,
Uh-huh.
10, 5, 9, 2.
2.
I think.
Double check. I didn't ask you to do the mental math, like I didn't force anyone to do the mental math with it.
This is faster.
Whichever one works better for us.
Yeah, it's right.
Okay. So that's the answer. That's the sum. We're adding up 5,296 twos, right? But see, we drew out another important understanding. Summation on a constant term. See what I'm saying now? Or it doesn't matter whether I is running from 1 to any number of terms again. See what I'm saying now? What was our general conclusion here? C times M plus N, right? You guys following? Okay. So we got a few of these special ones. And of course, YouTube, I mean, talking about YouTube, but Google has like a summation for an I cube, right? Here we went to a summation of an I square already. See what I'm saying now? But Google also has a summation of I cube, which is not very often that we have to use it. Okay, but if you want to do a Google search on that one right there, you're more than welcome to. And those are what I so-called the pocket reference. That yes, the Google is useful sometimes with that. Okay, but a lot of times you got to learn how to filter out your information. But now in the same example here, similar. Let me call that example number 4 right here. We still want to find the sum, but without adding the terms. But I'm going to have to make that into a more creative combination here. Alright, so part A, but example 4 here. It's very similar to to example 3 we've done. But now I'm going to, because it's along that way, that kind of problem, we don't want to add the terms. We still want to come up to the final sum without adding the terms. So I remember you guys had something like that. 2i plus 1, right? And then I is running from 1 to 100. See what I mean? Okay. So now if you write down the terms, first term is going to be a 3, right? Because when I equals 1, the term value is a 3. You guys agree? Okay. Next term over is going to be a 5, right? Next term is going to be a 7. So you're going to have 100 terms like that to finish. Or you would be like that. Right? And the last term is going to be 201. You guys following right there? So basically, those are all the odd numbers starting from 3s, right? And we adding up to all the way to 201 with that. But the point now is that if we're adding this, it's going to be very deadly. See what I'm saying now? Okay, so there's strategy now. There's strategy of doing this. We don't want to go that route. So the strategy here goes: one property that you guys can now check is that when you got your sum terms is in the form of a summation, it's also in the sum of some two other terms there. Okay? In a summation where each of your term is a combination of some two other terms, either added or subtracted, right? And you can break your sum into two separate ones. And that's one property that you can make use of. And of course, the indices run from 1 to n. Are we good? Okay. Then another property to mention for everyone is that when each of your terms is in the form of a coefficients times AI, and that's just the same as the summation. I mean, the constant C, the coefficient C multiplied with the sum on the AI term. Those are some important properties of regarding summations as well. And so here's the planning step. Because again, the point is we don't want to do the adding up the terms. Now allow me to erase this. Okay? Adding up is so deadly. So here I'm going to break that down. You guys see two terms here. There's a 2i plus 1, right? See that? So I'm going to break that into one summation on the 2i, okay? Plus a one summation on the constant term once. Are we good with that then? Right? Using that property I mentioned just now, we can break a summation apart as long as we recognize each term has a nature between, addition or subtraction between some two terms. Yes, 1 to n to 100, 1 to 100, right? So in the next step, don't you recognize that this is a coefficient 2 times I, right? So we can rewrite this specific sum here as the summation of just the I of that. That would be that, and then multiply with the coefficient 2, right? So I runs from 1 to 100 plus, and then the next one right here is the summation of a constant. I runs from 1 to 100 again. Are we good? Now you have all that tools. Now we have all that tools that you use. So what do I mean by that? This first sum right here, see, we've learned that special formula which is still here on the board, right? So that now gives me, so just the sum of the I here, we're looking at 100 times 101, right? Divided by 2, and make sure to multiply that with the 2 in front as well. This coefficient needs to be multiplied with the entire summation value. And then we got something else to go, right? So now I'm looking at summing up 100 terms, and they're all 1, 1, 1, 1, right? Now we're talking about plus 100 times 1. Okay. Now you're ready. The 2 here cancel. Those 2 cancel. So we're looking at the 100 times 102, so it's 102. So 10,200. That should be the final answer. Okay, go ahead and double check it that way. So let's look at another one. So now you see where I'm heading, where I'm going with that, right? So we're applying all the properties together, all of these known formulas together with the properties of summation to get the work done without adding up the terms. So think about exactly one like this. Right, part E right here, summation. Then you got 2i squared minus 3i plus 1. I going from 1 to 10. Just that. As far as the sums, as far as writing down the terms here, see when I was 1, we got what? 1 squared times 2. Right? And that first one right there, so 0 is the first term, right? And when I was 1, when I was 2, you got 4 minus 6. I mean, 8 minus 6 is 2 plus 1, that's 3 right here. You guys see what I'm saying now? Right? And then when I was 3, then we got that's 9 times 18, right? And minus 9 again, that's 9 plus 10 like that, and so on and so on. But you got a lot to go, right? So we got to figure out each term, and then we're going to add up all the terms because it's too much for us. So we're going to learn all the properties we've learned together. Of course, that route is out for us, right? So here we're going to go, see, 3 terms, right? There's subtractions, there's addition right there. So I'm going to break it down to one summation on the 2i squared minus the summation on the 3i, and plus the summation on the on the constant 1. See how it works with that? Right? And then of course i's go from 1, right, to 10. So now the next thing, see, now is the coefficient, right? So we go 2 times, right, of the I squared here minus 3 times the I term, right, and then plus, just that comes 1. Okay. Are we good with that? Okay. And yes, I goes from 1 to 10, ABC goes from 1 to 10, right. Right. So now we can utilize the things that those, these gonna have to deal with the formulas, right? Now with that one right here, running up to 10 right here, I'm looking at it. So just the I squared itself, it gives me 10 times 11, right? Times 21, you guys agree? Divided by 6. But don't forget, we have to now multiply by 2 this time in front to use that coefficient. Are we good? Right. And minus, now that's here gives me 3, right, times the 10 times 11, right, over 2. Are we good? Right. And then the last one here is going to be just 10 times 1, right? All right. So now we can start doing the math right here. Okay, so the 2 cancel with the 6 here, leaving a 3, and the 3 cancel with that, leaving a 7, right? So it's 77 times 10, so we're looking at 770. That's the first term right there, right? And then these guys over here, how do we cancel that? And that's canceled with that, leaving 5, and so 55 times 3. So minus 55 times 3 is
65.
What's that? 65, yes. Okay, plus 10. Right? So now go ahead and do that add and subtraction with that. It's a lot easier, isn't it? I mean, with some planning. So, go ahead and get the answer right here. One more time?
615.
615. 615. Look good? All right. And so, I can just pinpoint another problem right here, but we don't have to. We'll get into that, and then I can leave that for you guys here. But think about a problem like this. Okay. Let's produce the same one, 2i squared minus 3i plus 1, right? But now what happens if the index runs anywhere from like a 10 to 20? See what I'm saying? No? Okay. Sometimes things go like that, right? Sometimes in your sum, things instead of starting with I equals 1, right? Sometimes it starts at I equals 10 again, it runs to 20. See what I'm saying? No? So in a situation like that, what can we do? This is what you can do. You can go, this sum right here really is, and of course we don't want to add up the terms, so think about this, a long sum, the total sum going from 1 to 20, the longest sum right here. Okay? All of that 2i squared minus 3i plus 1. And then think about the shorter version, I going from 1 again, we're always going to reference back to 1, 1 to 10 this time. Okay? And then the 2i squared minus 3i plus 1, right? We do that, and we subtract out the 2. So you do your calculation on each of these and subtract out. You see what I'm saying now? That's the plan like that, or something like that. Okay? And then I can leave that for you guys to complete. You know what I'm saying now? So now on each of these, when as long as you already have your starting index to be from 1, right? And it's already easy, and you can just apply the formula similar to how we've done the earlier problems. Okay? So that's example 4. But still, there's more into the summation business here that I want you guys to get really comfortable with before we making our way back into the integral stuff. Okay? So you want to build that foundation strong. Otherwise, if your foundation on the summation goes loose right here, then the next one is going to be hard. Example 5 here, and maybe quite a few problems as well. Okay. So we want to write the general expression, okay? Write the general expression for given sum me just recall for everyone again that you see the one that we've had earlier when you got a just constant term right, on each of your terms together and running from 1 to n. And that's general final sum. We don't want you to go c plus c plus c plus c n times, right? The general expression is c times n. This is what I mean by the general expression. See what I mean? Okay? And so just like that, we have already seen a few other ones. Summation on all the I terms, right? I going from 1 to n. The general expression here is n times n plus 1, right? All over 2. This general expression here gives you the total sum without adding up the terms. That's the idea. Okay? And then another one I introduced, and then for the rest, you guys can Google search, right? I square, and then I go from 1 to n. Here we're looking at so n times n plus 1, right? Times 2n plus 1, right? And we divide that by 6. That's another general expression right here. General expression, right? For these, that's you can get the sum done without adding up the terms. Sounds good. But now we're not going to beat around for the example we're about to do it here. The point is, I'm going to show you how to utilize those very basic ones, right? And we're going to combine that into the larger problem. So how about you got a sum that's going from 7i plus 3, right? Then I is going from 1 to n. See what I mean? We want a general expression for something like this. Right? We don't want to beat around with the bush with those simple, way too simple, so basic ones. Okay. Right? And then we also have a couple rules and properties with summation that I wrote down earlier that we have to erase, right? That I have to clear out on the board. Okay. So what I see here is that we got each sum term is containing 2 separate terms again, correct? And so now my first starting step here, I'm going to break that down to 2 separate sums. One of them is for 7i, the other one is for 3. And we're adding up the 2 terms. Do you guys agree? Okay. And I here is running from, yes, 1 to n, 1 to n. Sounds good? Okay. And then, so, that's coefficient 7, my first sum right there. I can pull it out as a common coefficient. Now I'm looking at summation of I running from 1 to n, and then here is the summation of all the 3's, right? I running from 1 to n. Agree with that still? And so now, at this deep level, right, each one of these comes out from these known results. Yeah. Are we good with that? So now I'm looking at, I'm bringing out space. So here it is going to be 7 times, right? 7 times, and then there's a fraction. N times n plus 1 over 2. Are we good with that there? So the n times n plus 1 over 2 came out from this sum. And then the 7 times because there's a coefficient 7 in front of that. Right? And then, now we're moving over to the general expression for the last term right here. It's just going to be 3n. You guys following? Right? But ladies and gentlemen, this is that general expression I'm talking about. Right? We wrote some general expression, right, for a lengthy sum in terms of n, in terms of the number of terms. That's how it's done. All right. So the crucial key in any of these problems, you got to be able to recognize see, these are the constant part and the coefficient part, which is it's always going to stay the same throughout all terms, right? And then there's a changing component here, or the variable component, the one that changes value throughout each term. That's the one that gives rise to these basic formula, and then we're going to blend them together. See what I'm saying? So you got to spend your time identifying who's the changing component and who's the coefficient or component component. I mean, coefficients or constant component that stays the same all the time. Okay. And so, ready to try that into another one? Okay. So in this next one right here, let me introduce. What I have here is some a times m squared times I squared. All right. So in a problem that's so deadly like that, right? Variables all over A and M and I, right? But you gotta understand again, that's why I mentioned that in when we were in part A again, when you're looking at the terms of your sum here, right? All you have to do is identify which component here is the non-changing part and which one is the changing part. The I square is the one that's changing over term by term by term. But doesn't matter at what term A and M are here, once they're given, they're just A and M. It just stays the same actually. I mean, they're letters, right? They're also a variables, but relative to this sum right here, these stay the same. See what I'm saying now? Let's think about it. On scratch work, if you're writing down the terms, the first term is am squared times 1, right? Because I is 1. And the next term here is am squared times 4, because I equals 2. That's squaring that to give you a 4. That's why I'm seeing this as the changing component. Okay, the changing component versus these are the constant or coefficient components of that. Am I making sense? Constants, coefficient. Got me there on that again. And that's the reason why now, after some quick sketchy work again, now I can legally factor out the entire am squared in front, right? Of my sum and leave that just simply the summation on the I squared. Now that makes life a lot simpler. That's what I'm saying now. Now with the m being available here, right? With the m, with the a and times m squared, factor out in front, and notice, see, in the problem here, the good thing is that the m here and the m there is the same, but it shouldn't affect the way how you solve the problem. The main thing now is that we're going to handle this summation of the I squared, right? With that formula we already plot with that general expression. So now I'm talking about for that summation, it turns into m times m plus 1 times 2m plus 1. You guys agree? Okay. Over 6. But then don't forget, we have to multiply with that coefficient am squared in front as well. Okay? So that's the general expression we're talking about. Okay. It's in terms of m and a at the end. And then here's the thing. You can even, and like I said earlier, this m and that m, they are the same m, right? So m squared times m, right here, we're looking at the final one being a m cubed, right? Times m plus 1 times 2m plus 1, which is a lot shorter that I can fit it all into this small remaining space. Okay? That's the general expression I was talking about. So any summation that the way how you operate with that, there will be a changing component, right? The value changes or the variable changes depending on the I position, and then there's a constant or a coefficient. You can always factor those out, okay? Or keep them as a coefficient. Sound good? So that way, we can quickly see another one. Think of another one here. Right, I from 1 to n, okay? And here your coefficient goes a over n to the 4th, right? And then here I have I squared, okay? Something like that. And this one here you should be able to pick up on the fly very quickly. So similar to the earlier one. So now I can see this is the non-changing component, right? Coefficient, constant coefficient. Keep it out, a over n to the 4th. Being multiplied with the whole I squared, I from 1 to n. That's good? Okay. So in that way, now I'm looking at okay, a over n to the 4th, right? Times, there's now n times n plus 1, times the 2n plus 1 all over 6, right? So all together, then there's the n plus 4 here, so putting n to the 4th, so it's all 6n to the 4th in the denominator. You've got an, right, times n plus 1 times 2n plus 1. I should have also canceled that n away, but I decided not to for some not so intelligent reason. Okay? There you go. That's a general expression. Okay. Example 5 here. So now let's look at part D of the example. Right? Let's look at the summation of 1 over n times a 3i squared minus 4. Okay. So for this problem, yes, I can plus or identify, hey, in the whole expression right here, then the 3i squared minus 4 is going to be dependent on I, right? It's going to be changing depending on the value of I. The 1 over n is independent, right? That's the coefficient. You can bring it out in front. The 1 over n times the times the summation of the 3i squared minus 4. Yeah, that. And of course, I is 1 and further. So now 1 over n is kept as a common factor, right? This sum right here, when you focus just to that sum, now it got two terms, right? So we bring in our past understanding earlier. I'm going to break that down as one summation for 3i squared. See what I'm saying now? And one summation for 4. So that means distributing the 1 over n for each one of these, we're looking at. And then I can also pull the 3 in front of my sum right there, right? So that's making it all together 3 over n I squared minus 1 over n times the summation of 4. Of course, these are all I going from 1 to n, 1 to n. Okay. So we might work with that. And that's still not the general expression yet, right? So the I squared, now we have a formula, right? It's right there. So now I have 3 over n times, right? Now I'm looking at n times n plus 1 times the 2 n plus 1, right, over 6. And then minus, now I have, for this 4 right here, it's constant term, so we use that general expression like that. So it's going to be 1 over n times 4n. Right? So now we are so ready to clean up the terms here quite a bit. The 3 cancel with a 6, giving me a 2. Right? The n got canceled out. See what I'm saying? Huh? Right? And then the n here got canceled out. Now in the end, this is what I'm looking at. It's going to be n times n plus 1 times 2n plus 1 over 2, okay, and then we're subtracting 4. That's the final general expression that I was talking about. You guys see the intention of these kind of problems here? I mean, they don't have a purpose yet at this point, but you will see that purpose later on. Right now, I'm talking about just a skill. That's how math learns like that. A lot of times there are certain times that we got to spend time learning the skills. And when your skill is fluent enough, right, you're going to use that to apply it to some real concept. See what I'm saying? No? And so a lot of times back in the days that you learn the algebra, your teachers keep throwing you, hey, here's a skill, there's factories, a trinomial, factoring the polynomial, and you feel so deadly. I mean, why you keep questioning the teacher and why you got to learn this? This is where it all came back.